good. There seems to be a whole alumni group from Rochester here today. He got his master's and PhD at Northeastern University. After being at BBN for a while and founding some groups there, he's been most recently at IBM. He was senior manager for the quantum engineering group, where he had 86 engineers working for him, I guess engineers and physicists.
Yep.
Working for him. He's now quantum lead for new product development, new quantum development outside of New York. So he is the one responsible for installing the quantum computers in Japan and in Germany, and most recently, I guess, in Cleveland Clinic. And in addition to that, he's also an adjunct professor here at the University of Rhode Island. And I have hoped to see him permanently here sometime
Very soon.
fall 2025.
Yeah.
So it's my great pleasure, Crystal Walker.
Okay, so getting started, Len asked me to talk more about how quantum computing can kind of work with classical computing. And, you know, with a bent towards the computer science, you're going to get a lot out of this. So I went to a friend of mine who's actually in charge of that. And I said, what decks do you have? So I've adapted some of his things. First thing I'm going to do is this is my, what did I do last year? If you guys have not seen Quantum System 2, this was in your presentation. That contains 3 Heron processors. And today they are classically interconnected, which means that you don't have the quantum interconnects today. I call them quantum interconnects, but it's like a precursor to what was just talked about. And we're working towards, we have the demonstration of our short quantum interconnects, chip to chip. We have chip on chip, so from one edge to another. We're going to do chip to chip. And then my new project is actually working on what we call the L coupler, which doesn't go kilometers, but it will go a meter. This thing is upgradable. It's currently, so there's 3 133 qubit processors in there. This is upgradable to 4,000 qubits, superconducting. I'm going to skip over kind of the whole technology. I think Kushik gave a pretty good presentation on like what is basic quantum information science, and I will be focusing on this in particular. If you go and you talk to the executive VP of our group, this is their mantra. This is how he's trying to push IBM. And I kind of really believe in this. I think this is something that we as a society should probably start pushing towards. It's, you know, we've got traditional HPC, which has had GPUs, FPGAs, and kind of standard von Neumann type architecture processors. So that's the bit process. And what we need to do is we push forward to the future and think about more interesting problems that we want to solve. You want to bring in these other types of architectures, and that's what we say in the qubits and neurons. The neurons is kind of a funny way of saying AI. So I'm just going to focus on the kind of the HPC. Now, I just finished reading this book, which I highly recommend. It's called Turing's Cathedral. And it's written by George Dyson, who's the son of Freeman Dyson. So if you're physicists, you'll know who Freeman Dyson are. And he was at the Institute for Advanced Study when this machine in the upper left-hand corner was built. This is the Institute for Advanced Study machine, and it was the first von Neumann architecture machine. And why do I put this up here? Because if you look at it and you look at kind of, here's the instruction set over here, and you look at kind of what it had capable of, you know, there's 5 kilobytes of memory, and they use these horrible memory elements, and they developed some amazing algorithms. My favorite is this Metropolis Hastings algorithm, which today we know as Monte Carlo. And we use it all the time. Use it in financial sectors, use it in scientific sectors, and all kinds of other things. They did early weather prediction. This guy, Norman Phillips, he was a theoretical weather prediction person. When I was reading the book, I'm like, what? Late 40s, they had theoretical weather prediction? And the first genetic algorithm type studies and kind of a cellular automaton and things like that were done. And we're talking a very small instruction set. These people were highly innovative. So the stuff, this Metropolis Hastings algorithm, what they had done is they were modeling neutron cross sections so that they could make the hydrogen bomb. And they could only do like maybe 10 or 15 neutrons, but they were very clever about it. So kind of the takeaway I want you to get from this slide is, yes, we have some fairly imperfect machines, but you can be innovative. You are innovative like these people, you can make really interesting things. Turing's Cathedral. It's very well written. So I've already kind of said this, is that traditional HPC, at least the ones I've seen, I've been involved with, that you had a classical CPU of some sort, a GPU. I mean, FPGAs were used an awful lot. I don't see them used as much. It seems like it's easier to go get yourself an NVIDIA processor and slap it alongside, and life seems to be pretty good. And NVIDIA has done a great job at kind of figuring out how to do that channel of data transfer. So what is motivating us? I've had a few conversations today in terms of simulation cost, quantum circuits, complexity, and we are kind of on this green curve right now where we're trying to do error mitigation. We're pretty far away from error correction. When I say far away, I mean probably on our roadmap, I think we're actually supposed to deliver in 5 years. So it's not that far away. But you're going to see, we've been talking about, what do we call it? I like to call it quantum advantage rather than something else, because it's when the processor actually becomes useful to you to solve interesting problems. Because honestly, these other things that get put out there and saying, oh, it can solve this problem, it can't be solved on a classical computer, if it does not solve a problem of interest that is useful for, say, EB, they want to do something with it, then it's a useless device. It's not earning money for anyone. It's not creating value. The other gentleman that was in here in terms of talking about big world problems, you need to start to think about those. And this is kind of where we're looking at it. Once we cross that blue line, life gets to be really nice. So you can creep up the green line, or you can cross the blue line, and you're already way ahead in terms of classical compute. I wouldn't be IBM if I didn't flash up our roadmap. I think we're the only group that's actually pushing out that far. Since most of you in here are undergraduates, and I want to give you a flavor of what it's like to work inside a company. For all of us people that aren't in the upper management, you are basically going, I can't believe we have to actually do this. So it really makes you sweat when you start to see things like this. So we're kind of around here, and you'll notice that these number of qubits jump up a lot. So you're saying, well, actually, I think these are instructions now, and qubit counts change a little bit. And what we're looking at is kind of, when do you get into the area of error correction? And I'm going to be talking sort of at the upper level. This is at the lowest level. This is the hardware. Normally, this is where I live. I do a lot of engineering down at this level and helping the people do make the processors. So here's an example of using Quantum System 2 and breaking it down. So if you, as an average person, and you can do this today, you could download our program, and you can download anybody's. I don't know how well we interface with other people's software, but you've got something that would run on your laptop to help you. It's like a front end, IPC, whatever you want to call it. But it would allow you to program in, say, Python, and put together and pull in our libraries that you could say, I want to do variational quantum eigenstates, or I want to do whatever you want to do that we have a library for. And you would start to put together your program. You would then submit that. It would go out to the cloud, which is represented out here, and CPUs and GPUs would crunch on that for a long while, and then they would come up with a optimal gate set. Because if you just go straight out of a compilation of turning it into a series of C0 gates, which Kushar talked about, or Hadamards, or whatever you want to talk about, that spanning gate set, they might not be optimized, and it might take a very long time. And giving the coherence times that you have available to you, you might not be able to achieve that. But there are ways of saying I can interleave these gates in a funny way and they'll come out better. Now, I want to stick with variational quantum eigenstates. That's a very nice example of doing things. It is used predominantly for quantum chemistry. And one of the things, Kushar also mentioned this, that typically if you were to submit a job, you'd do what we call 1,000 shots. So you kind of average over the errors. The problem is if I have to go back out to the cloud and query the cloud as to what I'm supposed to do next, I mean, all you have to do is do a ping on like google.com and it's going to come back in a millisecond or two. If I have to do 1,000 iterations, I'm now at 1 second per round. So first time we did the lithium hydride simulation, it took 2 weeks of runtime. So and I'm building up to a story, so bear with me for a moment. So we developed this thing called runtime cluster, which is within a microsecond hop to the quantum computer. So it's very tightly integrated. So when you do this compilation, you actually break it up into pieces of saying, I'm going to do pre-processing, post-processing, runtime, and then the QPU. So that's part of, again, Kushar brought up this really nice thing about talking about the full stack. I mean, yes, he's talking about the full stack from a networking perspective. You have to talk about the full stack from a computing perspective as well. Well, I just said all of this in words. The same idea of you map the classical inputs to the problem, you translate the problem, and you optimize it, you execute, and then you do any post-processing. In post-processing, if you understand the fabric well enough, you can actually extract out some of the errors that are introduced. There are some things that are done today. They're calling them shares. But you can, and this is our heavy hex architecture. I remember talking to Michael earlier about this. This is kind of our standard way of laying out qubits. And we have qubit fabrics that are, say, we're retiring all of our 27 qubit fabrics, mostly going with home 33s. We'll get up to 1,000 very soon. But that does not mean that entire fabric behaves the same across every part of it. So in near term, we will end up dividing that into smaller pieces. And so you've got the whole QPU, then you might break it up and you say, I'm going to put multiple jobs of the same type. So I cut down on the number of shots. And then you can stitch them back together. Now, part of that also lends itself to saying, I can now get an early view on when I have multiple chips and I have to have the inter-process communications. So I can start to figure that out. Now, I don't know if I'll get into it. I can't remember. When Kushar was talking about you're doing some sort of networking between chips, and we'll be doing it, say, in the same cryostat. I think it's kind of irrelevant if it's inter-cryostat or not, or between machine-machine. There's a problem at that edge. And you're working on the right kinds of things of figuring out what are the protocols that we need to do that, because what you want is that to be transparent. And you don't want to say, I've come to the edge of my fabric, I'm going to jump to another fabric, but I've just introduced 100 milliseconds of latency because my protocols suck. So that's going to be a very important thing. And you want to say, and for us, I don't know when you're talking about it, how you look at it is you're saying, am I going to exchange a real photon, a virtual photon, or am I going to do a gate, or am I going to do an entanglement distribution? We haven't really decided what we're going to do with this is the best thing yet. Oh, sorry, here. So this is kind of no, I'm not sure I really want to talk about this. It gets a little bit into the economics of it. There's this thing up here called pay-go, which means you pay as you go. So if you were going to buy time on my machine, and this is like going back to when I was an undergraduate, you actually had to pay for time on the mainframes. Similar kind of idea if you want to run on us. But you come through and you have runtime, which I pointed out is actually a whole series of satellite processors that sit close. Here, it's right here, satellite runtime. And then I'm going to, for Michael's benefit, you've got this controller down here, and I don't remember if I see it in the slides. I refer to it as room temperature electronics. So everything up until about this point is actually in the digital domain. And it's very much like the type of programming and has the programming paradigms that you are used to every day in a classical computer. The last step, you have to, depending on the type of fabric you are going to excite, whether that be superconducting qubits or trapped ions or something else. In our case, it's superconducting qubits. You have to convert that to some analog system. So we have this room temperature electronics, which for all practical purposes is very sophisticated software-defined radios. Like for you, it would be ECM. And what you're doing at the satellite runtime is you're coordinating these controllers. For Michael's purposes, he and I were talking about optimizing the pulses that actually move you on the block sphere that Kushar showed earlier. You can do that. There's a toolkit that you can go through and you can define your own pulses. And so it would skip through all of the cloud stuff. It would go directly to this and then go directly to the controllers, where you would actually have a waveform, because you could say, I know, or I think I know how to do the waveforms better than you do. Otherwise, you're going to get our waveforms straight out of the box. This is more of what I was saying here in terms of the API and whatnot, but it's showing you a little more of how we go about things. I'm sorry about that. I'm kind of getting ahead of myself when I say things. Don't want to do that. Let's stick here for a few minutes. So this is where you kind of really get into the details of how we go through and do things. So going back, again, this is really optimized towards computer science of saying, okay, why do we need computer science people? I mean, if you look at this, I think you're immediately going to say, yeah, this is a typical HPC layout and process flow. The differences are the types of processes that run on there are a little bit different. So if you submit a job, let's suppose it's a job that's much bigger than a quantum computer, and you're trying to fork it out and say what part runs on quantum, there's going to be another part of this that is saying, okay, I've got the classical part, now I've got the quantum part, and then this is talking about the quantum part in particular, once you get down to kind of the optimized level here and execute. And then again, there's this handshake between the runtime nodes that I was telling you about and the quantum processor. Now, long term, we're talking about connecting many of these together in a data center type of configuration. That is, I will say, it's a very heavily debated way of laying out these data centers. And I'm going to keep paying lip service to Kushar's work because, yes, I was kind of harsh about saying I don't like quantum networks, but it is that. You do need it. And this is kind of, and once you get to this level, it's a must. There is no ifs, ands, or buts. What I view is going to happen is much like if you go back to the days when I was in grad school, there was no clear winner for how you were going to network things. So you had Ethernet, which was predominantly a Xerox, came out of PARC. DEC adopted it. And then IBM was pushing the store and forward kinds of thing. I can't remember what it was. It was a horrible thing, quite honestly. And I thank God that Ethernet won out. This is kind of what we use today. So let's talk, sorry, keep coming back to the VQE. It's a very popular one. It's easy to talk about. What's happening under the covers when you do this operation is you prepare some problem and you encode it. So how many people have done genetic algorithms or some sort of optimization like that? And people worked on optimization problems? No? Okay. Well, okay, you have. But so whenever you do optimization, VQE is no different than that, although the process is different. The really big hurdle in my mind is how you set up the problem. You've got to define it. very well and very carefully as to how you encode it. Because if you encode it poorly, it is going to take you a very long time. So you want to make sure you encode it correctly. Once you get that figured out, then you can actually ask the quantum system how to get these various thetas, or these angles that are going to end up minimizing the quantum energy state for the chemistry problem out of the system. And the way it does that is you will do something like this, where the classical system is going to keep track. So this would be runtime, the stuff that lives close, keeps track of those thetas. And then you might do something like the discrete Fourier transform over here, because the quantum processor is really good on it. Not sure I can really talk to this one. But it's kind of getting into a little more detail about how that is actually done. As I haven't been involved much with this. It's on the classical side, but you're trying to, as you do the minimization, you're doing the operations on the quantum computer, you're feeding it back to the classical, and you're saying, does this kind of head in the right direction? And then you do the next iteration. So again, I don't think this is hugely different. Now, there's been a discussion here today where you talk about, okay, it kind of sounds quantum, it kind of sounds classical. If you look throughout history, you will find we always grab the tools that we know best. So I'm going to go back to Kushar when he was talking. If you go, here's another good book I'll recommend. It's called The Victorian Internet. And it talks about the rise of the use of telegraphy. And the first form of repeater then was a human. Okay, if you could only go this far with an electrical wire, and the person would receive the message, and then he'd turn around to the other telegraph key, and then he'd key it back out again. So this is like the store and forward kind of notion. Then they got better, they introduced a relay, but it was like, okay, I'm going to have like 5,000 ohms on the input side, so I don't draw a lot of current because I can't flow a lot of current over, say, 20 kilometers, and then I'm going to regenerate it with a high current pulse. So we start with what we know, but then we bootstrap and we get more and more intelligent. And so one of the things I want to tell to like the undergraduate physics students, I think one of the things that happens to us is it gets beaten out of us. Don't be afraid to make mistakes, because we all learn. That's the best way to learn. Just dive in, start making the mistakes, and keep moving on. A lot of, again, a lot of these things are saying the same thing, but you've got this breaks down, and you'd have to talk to one of the people that actually wrote the software. We do have a fairly sizable software team that thinks about things and brings the real way of doing business to the physics side of the house. I'd say the physics side of the house lives over here, and the quantum computing people, or the classical compute people, live over here, where they're talking about, how do I break down the processes? How do I keep track of things? At some point, we're even going to have to talk well, there is some of it built in here in terms of scheduling, because even when you break things up on the fabrics inside here, when we're talking about using multiple quantum processors to run maybe the same job or multiple jobs at the same time, you have to keep track of all that on the classical side. And I will tell you, there's probably no physicist in our group that knows how to write a scheduler. So you want somebody who comes from the classical side of the house that can at least start thinking about that. I have kind of talked about that. We used to I call them libraries because I'm old, but now you always have to assign new names. We call them now these patterns. So when you load up your system, and again, talking to the computer science people, if you were writing a pattern for us, which would be in many ways, how many people have programmed in Python? Okay, so you know what it. So you do an import on something, and then you start using that. That would be like a pattern toolbox. You'd load up that toolbox and then you'd say, okay, I want to do the following, and you'd start doing it, and it would make the calls over the network to go out to the cloud and do all of those things that I just talked about, and eventually get back to the quantum system. Some of the other things that I'll just bring in that you have to keep track of, because I did talk about schedulers, and I've talked about how the fabric isn't uniform. So imagine now that I've actually got multiple processors. I've got multiple herons, or I've got multiple whatever is going to come, an osprey, or we've got a heron and an osprey in there. Again, I'm talking to IBM terms. So that's the 133 qubit and the 1092 qubit systems. And I've got them interconnected. The scheduler has to know about that and has to figure out, how am I going to deal with that? And I'm glad Kushar went first, because he kind of laid a lot of groundwork for things that need to happen. The whole idea of, you were talking about it in terms of the larger picture of how do I get that maybe across the nation. I'm talking about how I get across the room, of how do I make all these things talk well together, because you're going to have to know about the topology. And if the topology changes during the running of the program, you're going to have to redo the graph and then figure out what's the new topology. So these are all fun, interesting problems for those young people that are entering the field. Lots of good challenges. This is way too much of a sales deck. I apologize. You kind of know this. You get workflows, you turn them into Qiskit patterns. I've said all this. You deploy them, you run them. This gives an idea of what it looks like in terms of, here's the Python code. Nothing really scary at all, honestly. I think you should all do it. Any one of you could run on one of our simulators for free. And I think that the queue time on the simulators is too bad. For the free hardware, I think the queue time can vary anywhere between 6 hours and 4 days, depending on how badly somebody's monopolizing it. And I would encourage you to try that. I don't know enough about serverless to really talk about this well. This is talking about the max cut algorithm. How many people are familiar with max cut? Another optimization. So that's just another thing that you can pull in and try out. Okay, if you hit the QR code, you could download the details on this. As I said, this is unfortunately pretty heavily on the sales thing. I'm just reading the notes here, and apologize. But there's this thing they call serverless, and I kind of really hate when they dream up these new stuff. They're just recycling old words. Look, you can't get away from server. It just doesn't happen. You've got all kinds of standard server processors that are running. I mean, in reality, what you have are all these virtual machines with many processes running that connect all together. Now, I'm really focusing on you, and I'm sorry, I don't know your name. You've been asking a lot of questions like how sort of a young computer scientist person could get into this, and how would they contribute? Well, just because it's done this way, I'm not going to say it's the right way to do it. It is a way of doing it. I think there's a lot of advantage to young people getting involved, or computer science groups. And this is something that IBM, if you look most recently at the deployment, I was not involved with this one. We put a quantum system one in at RPI. And yes, Len has been trying to get one here. The reason RPI got one is that the co-founder of NVIDIA was an RPI grad and turned to the head of the board of directors, said, we ought to get one of those here. How much would that cost? And the bill was said, oh, I can afford that. So what they're doing is they have a fairly large compute cluster, and they are going to work on these kinds of problems of how do you seamlessly integrate HPC and quantum. Now, that just because you don't have one on campus does not mean you cannot participate in that. It's going to be a little slower. You can still do that development. One of the things I like to point out, also, I think I was a postdoc at the time, around the World Wide Web came out. And there was a guy, he had been hired as an undergraduate at UIUC to work at their HPC facility. His name was Mark Anderson. How many people knew who Mark Anderson is? He developed Mosaic as a summer student. And that's when it, the W3 standard was set up to be able to share physics documents. And it was clunky as all hell. And as soon as Mark Anderson came out with Mosaic, everybody looked at it and go, oh my God, I've died and gone to heaven. And so then, Mosaic begat Netscape, begat Explorer, and now the world is a very different place. So don't think that you can't do this. I was having a conversation with somebody earlier about math and classes, and I think one of the problems that people say is, oh, that's hard. Stop saying it's hard. More like, why not me? You should give it a try. Don't be afraid to fail. You don't know where you're going to end up. What I'm going to do is I'm going to stop early because I'm feeling like I don't want to sit here and advertise and throw all kinds of IBM garbage at you. That's not a really useful thing to do. It's more useful to give you a flavor for, yes, there is a very, very big role for classical compute problems to be thought of. And the other thing that I want you to walk away with is that thing I was talking about when I brought up the IAS computer, is the world is really your oyster. Just like when they built that machine, they started with a blank sheet of paper. Just because IBM and all those other, I don't know, there's probably 1,000 software companies out there that are doing quantum software. You should not assume any of those are correct. They may have bits and pieces of that puzzle. I'm going to give you another example. The sewing machine, which was developed more than 150 years ago, there were probably 10 or 15 companies that had patents on critical components to make a sewing machine. And it took Singer to buy out all of those patents and then put them all together. But Singer didn't come up with all those ideas individually. 15 or 20 different people did. So that when you go and you look at these other software companies, they've got a lot of ideas. You should look at those ideas and say, what are the best ones out of those, and come up with your own notion. I want to spend a couple more minutes because again, this is motivated by conversations we had in the Q&A session before this. What I think would be really useful as kind of a next step, Len and I have been talking a lot about this, and with Michael, I'm trying to get this ginned up, but I think it's something maybe URI can push this forward as kind of an extension of Quantum Day, is to go, we're talking at a very high level. Let's choose a few problems and work together on them and take them apart and say, how might we do this? And I think that would be more of a useful educational tool than kind of saying, well, you might be able to do this or you might be able to do that. You never know how those, we were kind of having a cross conversation of saying, we know how to implement stuff on our quantum machines, but we don't know enough about your application. So we really need to talk to people and find out what the applications are. And what I would invite, again, I'm creating a vision kind of on the spot here, is that the undergraduates and the graduate students are a part of that. So what you do is you say, okay, somebody like myself or Michael or somebody else, we would create kind of a vision, but then we would hand it over to the graduates and undergraduates and say, okay, have at it. We'll supervise you. Because that way you get the training on how you move forward on doing that, and it's going to be a real world problem. And then we can feed back to the theorists, say, hey, we couldn't do this, and if we could do the following things, it would be easier. So we just, to the point we had in the discussion, the way if we could implement better communication, I think would be really interesting. So a little short, but short and sweet is probably better than long. I could go on endlessly about this stuff and show you lots of other photographs and things about how we do error mitigation and whatnot, but I think it's better if we go to questions.
Thank you very much. We have questions.
What do you mean when you say fabric?
Oh, I apologize for that. That's pretty much a term I coined. I use it as an agnostic term to say, I've got a collection of qubits that are interconnected somehow. So then I say the word fabric, that could mean superconducting with a whatever interconnection method it is. It could be trapped ions where you have to shuttle them. It could be neutral ions in a lattice, doesn't matter. But that's the fabric in which we operated on. And one of the things that I believe right now, this is kind of a funny thing. If you look at it, all of us, all the competitors in the field, we have these fabrics without really any structure on them other than what's mitigated or demanded by physics. There's, if you look at it, even the IAS computer, they created what they then called, like today we call it an ALU. They called it an arithmetic organ. And we don't have any notion of that today. So today, when we want to do those kinds of operations, you actually have to write a pantload of code in order to actually enact that rather than having it happen on the fabric. So there's a nice, interesting challenge where the physicists and engineers should be working together to figure out what is the architecture that looks like.
So, would an ALU for the quantum be all-to-all connectivity of equal?
So I will not answer for IBM. I'm going to answer for me personally. Yes. So if you look at, and I'm always going to get stuck. And you brought up a really good point. I just want to keep focusing on this. You said, where's the quantum and classical? I'm very classically trained and motivated. And if you look at the early days of parallel computing, I think it's even true today. If you can get all to all, you win. It's true of qubits too. If you can get all to all, if you look at, let me digress for a moment on the superconducting qubit. So I've got a fabric, I lay out qubits and they're kind of in a grid, but they have the connectivity of what I call the heavy hex. I want to implement some calculation on that fabric. What do I do at the edges? If I want to do error correction, if I want to do anything, error correction is fundamentally an algorithm. Once I hit the edge, all hell breaks loose. So when we came and we talked about on-chip interconnects, now I can connect this edge to this edge. The first thing that happens is you roll this into a cylinder, and then you connect the other two edges, and all of a sudden it becomes a torus. Now, mathematically, you've just opened up a whole world of error correction by going to a torus, because the way you travel around that mathematically and you enable that connectivity is really fascinating. So that's how so you talked about LDPC codes. So the current codes that are being worked on at IBM are LDPC inspired, along with being able to put them on a torus.
I was so happy for your last mentioning about the student extending for the quantum date with the URI student. So I was curious if IBM as an organization, are there any resources made available for such as students, other people who want to get their feet wet regarding quantum computing, coding, and such and such?
I am sorry to say that it comes at a cost, which is unfortunate. So this is kind of why I'm here. I believe that's a really important thing. So I'm putting my money where my mouth is, that I'm spending time with Len, trying to figure out how I spend more time here at URI, so that even though there's benefit to doing what you say, that I get the ability to reach back inside of IBM and say, hey, Kristen, you owe me a favor. Can you come talk to these guys?
I should point out that we do have an agreement with IBM where we have direct access to their quantum computers.
But not, that you don't have access to the researchers, which is, that's a tough part, and that's kind of an important part of this.
All the way up to the offspring.
Right.
is available.
Now, Michael, on the other hand, can go through the AFRL hub, and you can get access to the researchers.
Mentioned earlier something about a free access to the queue and everything, what is that something that we have, everybody has access to?
Yes. So there's a lot of online videos. I always find, basically YouTube is your friend for almost anything you want to learn. There's a whole IBM channel, a lot of really good information on there. It'll tell you how to set up Qiskit, how to get access, how to figure out what queue to get on. And then if you want to work with Len, he can tell you which queue to get on there.
And we have to point out that our certificate program that we have, our undergraduate certificate program gives participants the opportunity to use Qiskit and get directly on there, and they do programming as part of their program. And so that's another way to get familiar with it.
But really jump in with both feet. Do not worry about breaking the machine, because you're not going to. Well, I should caution myself. I always, whenever I say, "Oh, we'll make this foolproof," and I'm like, "No, fools are so clever." Yes.
6 hours to get from skip.
So if you go on the free queue, it depends on, everybody's using it. A lot of people use it for teaching class. I think Ike Schwang uses it for teaching class up at MIT. And sometimes you'll get someone in there that'll actually put like a really serious job, and it will just eat time on the queue, and we don't kick it out. We just let it run. So that sometimes takes the queue length and really makes it crazy. As a paying member, you should never see more than 30 seconds to a minute of wait time.
And all URI, everybody with the URI ID can get onto that computer. You have to fill out some paperwork, but everybody has the opportunity to do that. So if you want to know how it works, you can try out on Qiskit, which is a public access. But if you want to get onto the actual machine, you just need to fill out a couple forms, and you're all set to go.
So I think that most people in here are engineering or physics or something like that. I really want to push that. We had a conversation about this earlier in Len's office, that really everyone should have some working level knowledge about this. So, encourage your friends that are outside of this. Will come someday. Don't be caught unaware. Even if you end up in a procurement office, you should at least have, oh, I understand what that term means, and I can protect my company from being bilked because they're saying stupid stuff.
I guess I kind of have kind of a question, kind of an issue. Some of I went to a workshop the other day where quantum physicists refer to themselves as like quantum evangelists, things like that.
Yes.
And we have terms like magic and to describe like Clifford versus non-Clifford gates and all of those. How do you, from the other side of things, do you see that as an issue that needs changing to get it to like bring this to the wider public? When I go to EB and I talk about magic, they're not going to take me seriously.
They say electromagnetic interference is also.
Right, but so how do we change that to get it to the wider audience, or should we change that?
So I'm going to answer that in two ways. One, I'm no longer a manager, but when I was a manager, I used to encourage people to make up terms because it makes the job fun. And so like early days when we were making qubit fabrics, I would tell people, oh, you're going to make a line of systems, name it. One of the guys came up with the name Mothra, which never saw the light of day, but it made him happy, So he was going to go follow this whole Godzilla chain, and I'm like, okay, that's clever, it's interesting, it's fun. But to your point, yes, I think other people don't take that very seriously. But you're talking about like, I think of a magic state as a distillation. And that's very old. That's like, got to be what, 15 years old?
Yeah.
I don't know, you change that. But I think that to your point also, even the concept, when you brought up distillation in terms of the protocols, it's the kind of the same idea as inside a quantum computer when you're going to distill a magic state. It's like, what does that mean? And why do you even have to do that? That's a very long explanation.
I guess it just kind of speaks to the jargon, you know, at one point, my friend Luke and I were talking about how maybe we should, everyone's calling themselves quantum evangelists, maybe we could make like Martin Luther and nail our theses to the wall of IBM, something like that. But
well, one of the things I worry about when people say they're evangelist, usually they tack on that name, and that means they know just enough to say the right words, but they don't know what they mean.
do you see it as is that the direction that like the that quantum is going in, where we come up with these terms and then have to like work our way back to explain it to people that are actually gonna.
I don't know that we have a choice. So one of the ones I think was one of the worst decisions ever made, brackets. Okay, that dates back to Heisenberg, right? And the story as I heard it was Heisenberg invented all of matrix mechanics on his own. And then somebody said, do you know about linear algebra? I'm like, oh no, what is that? So he invented all this own terminology instead of saying inner product, outer product, and all that other stuff. And so you go and you talk to, I remember when I was working at BBN and I'd talk to people and I said, oh, you're at signal processing. It's the same thing. It's just different notation. Well, why is it different? I said, because we're physicists.
So they also, they're gonna declare, or they have declared at this point, next year, the International Year of Quantum. And so, one of the, essentially, the goals of that year is to kind of do what you said and make people not hide behind the fact that it's quantum, and try to get the word out.
This is kind of a really good point you're raising. I had this conversation at dinner last night with a friend who was bringing up the same thing. And he said, well, you guys are creating an elitism, and that's a disadvantage.
Right. And like the term evangelist to me is like, yeah, it's creating in groups and out groups. Like if you're not an evangelist, then you're a heretic.
Yeah.
Like, and so it makes no sense. And so I guess, you know, in grant, but I would like it if.
I want to see, what is the way we can get this down into the grade school level, that people can have terminology they're not afraid of, and at least have some, maybe you don't understand everything behind it. Like I learned commutation when I was in 3rd grade, I think. I don't think I fully appreciated it until I got to grad school. But at least the term wasn't brand new to me. It's just that, oh, operators don't commute the same way as numbers do.
That's a good starting, like when I've talked to engineers about it, that sort of thing's a good starting point, because they know that sometimes things don't commute because they've learned it early on. And so the fact that that's so fundamental for us is. You know what, when I talk to people and they don't quite get it, I say, well, have you ever looked at graphics, or have you done a rotation? Oh, yeah. I said, so, and sometimes I'll physically do it with my body, and I'll say, so you remember, you can do an X and a Y, but you can't do YX. You're going to end up in a different position on the screen. Yeah. It's commutation. It's no different than what we do. In fact, wow, these things that called the spinor matrices, same matrices. You're just doing the same rotations. So there's no great mystery about it. So I always try to come in from a computer graphics standpoint
and explain it that way because people get it faster. You don't say, well, sigma X, sigma Y, sigma Z. You say, rotation about X, rotation about Y, rotation about Z.
I'll put a plug in for the book, Quantum and Pictures, that we've been looking at. Which if you want to demystify what's going on, that's one way to do it. And it's aimed at, probably middle school or high school students, but if you look at it, it has some very surprising results that give insights. I mean, several of us have it, give insights that we hadn't thought about before. And talk about demystifying quantum. Set it up for, it's got spiders and various other types of characters in there.
So since this gentleman back here in the pink shirt is from BVN, somebody he's long since gone, but when I was there, his name was Wally Furtzwig. You familiar with the name? So he was basically an emeritus, and he used to hang out in the cafeteria and talk. And what he did in his early days at MIT is he invented this computer language called Logo. Anybody familiar with Logo? So it was the idea that Wally had in the 60s, which is pretty advanced at the time, was how do we teach computer science to kids? And it was really simple. He had this thing called turtle graphics. And then later you could actually buy turtles and you could program them. I mean, this is all meant like the early days of, you look at something like Lego Mindstorm. That's kind of an outgrowth of that whole concept. So to Len's point, that's something that we should probably try to figure out how to do. I hope I've amused you at least.
Vacations, in what sectors of the economy are buying quantum computers?
So probably our biggest customer is Fidelity. Well, so what they're the example I like to give with Fidelity, probably 20 years ago, one of the things that they did is they lit up a dark fiber between the Chicago Board of Trade and their main office in Newark, New Jersey. And the idea was they wanted to gain a millisecond or so on trades. So small changes for them have a big difference. And they are, out of all the companies I've interacted with, they have a very deep knowledge of quantum computing and are trying to figure out. So if you look at options modeling, traditionally the way they have done options modeling is they'll take the heat equation and they will say, okay, we're going to imagine it as a diffusion through a medium, and we're going to use options of similar types to predict options we don't know about to create the numerical values. So they want to say, can we do that, but on a quicker rate, and can we do it on a quantum computer? That's a application they're thinking about. That would be a game changer for them if they could gain another microsecond or two in terms of their trades. So it's kind of weird, but
That optical fiber is interesting because once they did that, other people competed and they all started trying to get closer and closer because even microseconds make a difference. And so finally, I guess the Securities and Exchange Commission set it up so all of the fibers would have the same delay time. But all of them tried, just moving, I'm gonna try to get closer, and they tried to get in the building next door, and they kept trying to move closer and closer.
And then what happened was that I think that right after that there was all these like micro trades going on, and they had to close the exchange because things were happening too rapidly. And so the Exchange Commission came in, they did that, and they put in intentional delays to act as a capacitor so you couldn't trade too fast. But other applications, applications is something I don't think we talk about enough. I am very afraid. I know somebody brought up CFD today. I'm really concerned that I don't see a path forward near term to how to get to CFD based on what we have today. So I'm really cautious about that one. But other things, I'm a big fan of, we should develop a signal processing toolbox, because that's not, I mean, somebody was talking today about simultaneous solutions of linear equations. That's a good one. You can do differential equations really well. Anything you can think about where you can formulate it into a Hamiltonian type of configuration are good problems. And when we brought Quantum System 2 online, and I had to give a tour the next day, so we did that on December 6th. And December 7th, I brought them through, and I'm talking to them, and I said, okay, I'm going to take you on a science fiction flight for a moment, because people were asking questions about, could you potentially see high data flow? Today, that's not a good thing. Again, going back to what Kushar brought up, is typical run is about 1,000 shots to solve a problem. But imagine that you do error mitigation well enough that you can actually get a solution that you feel comfortable with in 2 or 3 shots. So our rate at doing a shot right now is kind of on the order of 3 or 4 microseconds, which is not that long. So if you could then say, okay, instead of doing 1,000 shots for one thing, that at a, say, 1 megahertz rate, I can feed large data frames. Now you can start to think about doing image processing and some of these other large data problems. By the way, you know, in machine learning, yes, it's good for once you have your PDFs. It's not a very great way to make the PDFs, because PDFs have to sift through a ton of data. Everybody know what I mean by PDF? Probability density function. So in a lot of, I'm not fully versed in machine learning, but I have to believe that it's still very traditional, where you have very large volumes of data. If you look at Google and IBM and Microsoft and other companies that have like ChatGPT, how did they get there? My guess is, if you looked throughout history, what you will find is they bought a lot of companies that gathered a lot of data. IBM bought the Weather Channel, not because they wanted to own the Weather Channel, but they wanted a huge data stream, and to be able to get very large data sets that they could then reduce into hypotheses. So those hypotheses then become PDFs, probability density functions, that you can then operate on when you ask a question. You say, so this is, you know, typical detection, location, and characterization problem for Newick. What is my best probability of getting the right answer? And now those, like ChatGPT is, what I've played with, is pretty darn good. But it really is based on large data sets. And until we solve the problem of how do you get I/O in and out of the machine, that's going to be a while.
Could you use some like quantum sensing techniques in that, where, you know, you have things like the quantum frame bounds?
I think so. If you, so I know a number of people here know Saikat Guha. When I was still working at BBN and he was there, that was something that he spent a lot of time thinking about, of how, like, if you've got an image, how could you qualify that image with the minimal amount of information? So he wrote a couple of papers specifically using Kramer-Rao bounds. Saikat Guha. He's at the University of Arizona now. I'll spell it for you, or you know. I really want to encourage the undergraduates to get excited, though. Thank you for your time.
Thank you.